Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Klepner and Kolenko. We will continue to discuss topics from Chapter 6, Angular Momentum and Fixed Axis Rotation. In the last class, I have introduced the concept of angular momentum, which was defined as the moment of linear momentum. In today's class, let's get familiarized with another important parameter that characterizes angular motion. This is known as torque, which is defined as moment of linear force. Okay. So if you have a point mass at this point which has some sense of rotation about this origin, let r be the position vector of the point mass and F is the force acting on it, and this is the direction of F, then torque tau is defined as R cross F. Since this is a cross product, you can notice that torque is perpendicular to both R and F. Okay, so if you take the rotation happening in the XY plane, then the torque is going to be in the perpendicular direction, in the Z direction. If you look at the magnitude of torque, then if phi is the angle between R and F, then this is going to be RF sine phi. And just like we have done in the previous class, you can either define this as a product of perpendicular distance and force, that is R perpendicular F, as shown in this figure, or you can also define this as the perpendicular component of the force and the radius vector r. Okay. Alternatively, you can also define this cross product in terms of the vector components. So if you write r vector as xi cap plus yj cap plus zk cap, and force F in terms of its components fxi cap, fyj cap, fzk cap, then you can define tau as tau in the form of a determinant. One thing you have to note here is that torque and force are completely different quantities. First thing you can note here, from the very definition, it's clear that torque and force are perpendicular to each other. Secondly, just like angular momentum, torque also depends on the choice of the origin. On the other hand, force is independent of the origin. Since these two are completely different, you can have systems where the net force is zero, but there is a non-zero torque acting. Similarly, you can also have scenarios where the net torque is zero, but the force is non-zero. So I can illustrate this with two simple examples. So look at this system. So you have two forces acting and you have some sense of rotation about the center point. Now let's calculate what is the total linear force acting on the system. I have force in the upward direction, equal force in the downward direction. These two cancel, so the net force is zero. And what about torque? So torque is R cross F. So you place your right hand in the direction of R and curl your fingers towards F, then the direction of thumb gives you the direction of the cross product. So in this case, your thumb will be pointing out of the plane of the screen. So, and since R and F are perpendicular, you can replace the cross product with a normal product of their magnitude. So you have RF pointing in the outward direction. And what about the torque for this component? Once again, you find the cross product, you will find that it is directed out of the plane. So you have two RF components pointing out of the plane. So the net torque is 2 RF and the net force is 0. So these two are completely different. On the other hand, if you take a system like this, you have two force components pointed in the downward direction. So the total magnitude of the force is 2F. And what about the torque? So for the left side force component, we have seen in the previous case, this is RF pointing out of the plane. On the other hand, for the right side force component, when you determine the direction of the cross product, you will find that it is pointing into the plane of the screen. So you have two torque components, one out of the plane, one into the plane. They have equal magnitudes, which means they cancel each other. So you have net torque being 0, but net force is non-zero. So these two examples clearly show that torque and force are completely different parameters. Next important question, what's the relation between torque and angular momentum? So we know that angular momentum, L, is defined as R cross P. So you take rate of change of angular momentum, dL by dt is going to be d by dt of R cross P. Apply the product rule, dr by dt cross P plus R cross dP by dt. And look at the first term, dr by dt, rate of change of position is nothing but velocity v. P is mv. So v cross mv, m is a constant, you can take it outside the cross product. So this is going to be m into v cross v. We know that cross product of two similar vectors or two parallel vectors is going to be 0. So first term becomes 0. What about the second term? dP by dt, rate of change of momentum is nothing but force, right? This is what Newton's second law tells us. So you have R cross F, which is nothing but your torque. So torque is nothing but rate of change of angular momentum. So you can write torque tau equal to dL by dt. From this relation, you can quickly note that when tau equal to 0, dL by dt is going to be 0, which means L is a constant. So when the net torque acting on a system is 0, its angular momentum remains a constant, or angular momentum is conserved. This is known as conservation of angular momentum. This is very similar to conservation of linear momentum we have discussed in chapter 1. There we have seen that when the net force acting on the system, the external force acting on the system is 0, the linear momentum remains conserved. So these are similar concepts. Now conservation of angular momentum is a very important aspect when you analyze central force motions. If you recollect, most of the important forces which we encounter in the universe are central forces like electromagnetic force or gravitational force, etc. And it's particularly important in the study of planetary motion because planets move completely under the influence of a gravitational force field, which happens to be a central force field. So planetary motion are governed by three important laws given by Kepler in the 17th century, and the second law of Kepler is known as law of equal areas. And this law states that area swept out by the radius vector from the sun to a given planet in a given time is same for any location of the planet in its orbit. For example, let's look at the rotation of Earth around Sun. We know that the orbit is not circular, it's an ellipse. So this is the orbit. So suppose Earth is at this location. In 1 second, it moves from this point to this point. So the area swept out by the radius vector is this area. Okay, area enclosed by these dotted lines. Now imagine the Earth is at this position, and then in 1 second it moves from this point to this point, and according to Kepler, this area is going to be exactly same as this area. But this is counterintuitive, right? Because we know that this distance is more, so our intuition tells us that this area is going to be bigger compared to this area because here the radius is small. So let's now try to understand what is the physical basis behind this argument. As I said, gravitational force is a central force. It has the general form F is equal to F of R cap, where F of R is a scalar function which depends only on the distance vector R. and r cap is the unit vector, which is defined as vector r divided by its modulus. And since this is a central force, there are only two directions possible. Either it is towards the center or it is away from the center. For example, if this is sun and this is your earth, and if you choose your center, if you choose your origin on the sun, then you know that if sun is heavier than earth, then the gravitational force is towards the sun or towards the center. On the other hand, if earth is heavier than sun, then the gravitational force is going to be towards the earth or away from the center. So these are the only two directions possible. So these are the fundamental characteristics of a central force field. Now let's calculate what is the torque acting on any particle moving in any central force field. Okay. So we know that torque tau equal to r cross F. Since F is a central force, we know the general form for it. So this can be written as r cross F of r cap. F of r is a scalar function. Take it outside the cross product. So you have F of r into r cross r cap. R cap is nothing but vector r divided by its magnitude. Once again, the term in the denominator is a scalar. Take it outside. So you have F of r divided by r cross r. Cross product of two similar vectors is going to be 0. So this term is 0. So the torque acting on a particle moving in a central force field is 0. What is its physical implication? We know that torque is nothing but rate of change of angular momentum. So when torque tau equal to 0, it means dl by dt equal to 0, which means that L, angular momentum, r cross p, is a constant. So this is the first implication of motion in a central force field or a planetary motion. So in the case of planetary motion, the angular momentum of the planet is always conserved. This is the implication of motion in a central force field. Now, when I defined angular momentum in the previous class, we have seen a particle rotating in the xy plane, and we have seen that if the motion is in xy plane, then the angular momentum is always along the z direction. In particular, if it is moving in the counterclockwise direction, the angular momentum is always along the plus z direction. Let's look at the converse scenario. I can also say that if an angular momentum is along the plus z direction, then the particle will be rotating in the xy plane in the counterclockwise direction, right? So that's what the second implication of planetary motion, or second implication of motion in a central force field. Since L is a constant in both magnitude and direction, motion of the planet is confined to a single plane. Now what is the third implication? So we know that angular momentum is a constant. So angular momentum L is defined as r cross p, or m into r cross v, or if you look at the magnitude, since r and v are perpendicular, you can write it as mrv. So mrv is a constant. So once again, take the case of Earth rotating around the Sun. So let's look at two positions, position 1 and position 2. At the velocity and position of Earth at this point 1, let it be r1 and v1. And at this location, the velocity and position be v2 and r2. Now, according to conservation of angular momentum, the angular momentum at this location, point 1, is same as angular momentum at point 2. So I can write mr1v1 equal to mr2v2, where m is the mass of Earth, which is the same at both the locations. So I can cancel m on either side. So I have r1v1 equal to r2v2. Or I can write R1 by R2 equal to V2 divided by V1. Now we know that from this figure R1 is greater than R2. And what is its meaning? When R1 is greater than R2 from the equation, it means that V2 is greater than V1. Now you can understand the law of equal areas. So when Earth is in this position, in 1 second it moves an arc distance of this much. Okay, from this point it moves this much, and this is the area swept out by the radius vector. On the other hand, when Earth is in this position, here we know that the magnitude of the radius vector is small, which means the velocity is higher. So in 1 second it will be able to travel a larger distance. Consequently, the area swept out in this direction is going to be exactly same as the area swept out in this location. So planet moves faster at the point of closest approach to the sun. So since area A is equal to area B, we can say that the rate at which the area is swept out, if I denote area as A, then the rate at which area is swept out, this is dA by dt, it is known as aerial velocity, is a constant. This is what Kepler's second law is all about. So this is not only true for planetary motion, it is true for any motion of particle in a central force field. So let's look at the general theorem. For a particle moving under central force, rate at which area is swept out is a constant. So let's try to prove this using more rigorous mathematics. Okay. So let's assume that at a time t, this is the position of the particle in the central force field. Since this is a rotational motion, let's resort to the polar coordinate system. So at this point, the coordinates of the particle are r and theta. And after a time delta t, the particle has moved to a new position where the polar coordinates are r plus delta r comma theta plus delta theta. Okay. So basically this angular distance is going to be delta theta. This is r of t, this is r of t plus delta t. Now for small values of delta theta, you can approximate this to a triangle, right? Even though this is an arc, if this angle is very small, then you can approximate this arc to a straight line. So you have a triangle. So this angle is delta theta, and this side is going to be r plus delta r. And what about the third side? If this is delta theta, this side is r, and this side is going to be r delta theta. Okay. So you have base of r plus delta r, which is this side, and height of r delta theta. So this is a triangle. Now you can calculate what is the area. Let me call this area as delta A. Area of a triangle is nothing but half BH, half into base into height. So this is going to be half into base, which is r plus delta r, multiplied by height, which is r delta theta. So expand this product. This is half r square delta theta plus half r delta theta. Now, what is the rate at which area is swept out? So we have defined this as dA by dt. This is your aerial velocity. So dA by dt is nothing but limit delta t tends to 0, delta A divided by delta t. So we know delta A. So you can now calculate delta A by delta t in the limit delta t tends to 0. So this is going to be limit delta t tends to 0 half r square delta theta by delta t plus r delta theta delta r divided by delta t. Now look at the second term. The delta theta term is very small, and if you look at the figure once again, what is delta r? Delta r is nothing but this small distance, right? So when delta theta is going to be very small, this small distance, this is going to be even smaller. So basically in this term, you have product of two extremely small quantities. So this term is going to be even smaller. So for all practical purpose, I can approximate it to 0, which means dA by dt now becomes limit delta t tends to 0 half r square delta theta by delta t. Now limit delta t tends to 0 delta theta by delta t is nothing but d theta by dt. So my aerial velocity dA by dt is nothing but half r square d theta by dt. Since we are talking about angular motion, everything is specified in terms of polar coordinates. So let's also define the velocity of the particle in terms of the polar coordinates. We have done this exercise in chapter 1. So we know that we have two coordinates r and theta. Consequently, we have two components for the velocity. Radial component Vr, which is nothing but r dot or dr by dt. And you also have an angular component or a tangential component v theta, which is given as r theta dot. So this is along the r cap direction and v theta is along the theta cap direction. So velocity is going to be a vector sum of these two. So I can write in polar coordinate system vector v equal to r dot r cap plus r theta dot theta cap. Now using this definition, let's now calculate angular momentum of the particle. Angular momentum L is nothing but r cross p or r cross mv. Radial vector r in terms of polar coordinates is nothing but r cap, where r is the magnitude of the radial vector. Cross product m into r dot r cap plus r theta dot theta cap. So what's the cross product with the first term? Basically you have r cap cross r cap. Cross product of two similar vectors or two parallel vectors is going to be 0. So the first term vanishes. So you have only cross product with the second term. So which is going to be m r square theta dot. What is r cap dot theta cap? This is an orthogonal system, right? So cross product of two unit vectors will give you the direction of third one. So r cap cross theta cap is nothing but k cap. So L vector, angular momentum vector, is nothing but m r square theta dot k cap. Or if you look only at the magnitude, since motion in the case of xy plane, angular momentum is always along the z direction. So I indicate it as Lz. So magnitude of the angular momentum vector Lz is going to be m r square theta dot. Now let's rewrite dA by dt in terms of angular momentum. We know that dA by dt equal to half r square theta dot, and from this expression I can write r square theta dot is nothing but Lz divided by m. So now I write dA by dt equal to Lz divided by 2m. And look at here, look at this expression. M is a constant, and in the case of motion in central force field, we have shown that angular momentum Lz is a constant. So since we have all the constants on the right hand side, it follows that dA by dt is a constant. So we have proven Kepler's second law, which he originally designed using empirical observation. Now we have proven this theorem using the principle of conservation of angular momentum. Now what we are going to do is we will take a couple of simple physical scenarios and check whether this relation tau equal to dL by dt is true, whether this holds true in such cases. Let's start with the first example we have dealt with in the previous class, that is a sliding block. So consider a small block of mass m sliding in the x direction with velocity v equal to vi cap, and we need to calculate the torque acting on this sliding block and check whether torque is equal to rate of change of angular momentum. So in the previous class we have shown that angular momentum about this point, the origin point, this is 0. So there is no point in talking about torque with respect to this origin. And in the last class we have seen that there is a non-zero angular momentum about this point B. So if you call the radius vector as RB, so LB can be defined as M into RB cross V. So RB you can resolve into a parallel component and a perpendicular component, and cross product with the parallel component is going to be 0. You need to bother only about the cross product with the perpendicular component. So, and when you do that you will get MLV K. So this we have done in the previous class. Now what is the corresponding torque acting on the system? If the block is sliding freely, then there is no friction, nothing acting on the system, which means V is a constant. If V is a constant, then L is a constant, M is a constant. So all these terms are constant. That means LB is a constant. If L is a constant, then torque, which is defined as dL by dt, is going to be 0. So there is no torque acting on the block if the block is sliding freely on the surface. On the other hand, if there is some friction exerted by the surface onto the block, what happens? So let's say that the frictional force acting on the block is F is equal to minus Fi cap. So this force is acting against the free motion of the block, which means the block is going to slow down. Now let's calculate what is the torque acting on the system above the origin B. So look at the geometry here. So this is RB and you have a frictional force acting in the minus X direction, and torque tau B about origin B is defined as RB cross F. So once again you have to resolve into parallel and perpendicular component, and cross product with the parallel component will vanish. You have only the perpendicular component whose magnitude is L, and force F is given by minus F. So when you do the substitution you will get this as minus LFK. So angular momentum is in the plus Z direction, but the torque is acting in the minus Z direction. And torque is nothing but rate of change of angular momentum, right? So which means the angular momentum is in the plus Z direction, but the change in angular momentum in the minus Z direction. So as the block slows down, its angular momentum is going to decrease. That's the meaning of it. Now let's check whether tau equal to dl by dt in this case. So dl by dt is nothing but, since we know the expression for LB now, I can calculate dl by dt. This is ml dv by dt k cap. Now from Newton's second law I know that m into dv by dt, this is nothing but m into a. So ma is the force acting on the system. Here the only external force is the frictional force, which is given as minus F. So m into dv by dt equal to minus F. So in this expression, instead of m dv by dt, I can plug in the value minus F here. So this equation becomes dlb by dt equal to minus LFK gap, and minus L of K cap is nothing but your tau B. So we have shown that dLB by dt equal to tau B, rate of change of angular momentum equal to torque. So in the next class we will take a couple more systems, and we will go on to prove that in all the cases the rate of change of angular momentum is going to be the torque acting on the system. Thank you.